Thank you, Joachim, for the very nice introduction. And thank you all for coming for this nice last talk of the day. I hope it's going to be entertaining and that you can all enjoy it. So, as Joachim said, I'm going to talk about a new experiment that we are currently designing at Columbia University. It is called the Columbia Stellarator experiment, or CSX in short. And before I start, I'd like to thank all my co-authors, especially Elizabeth Paul and Carlos Paz-Soldan, both PIs on this project. And then all the names that you see here below are all the graduate and undergraduate students that are working on this project with us. So this is really an amazing project to work with so many different people, and I thank them dearly. So CSX, optimization of CSX, I'm going to talk about both engineering constraints, especially physics objective and optimization, and I'm going to try to walk this thin line between those three topics. And to start with, I want to make the point that this community, and I think stellarator research in general, would benefit from more experiments. To stress this point, I'm going to show you a Venn diagram that you all know, basically trying to categorize all kinds of 3D magnetic fields. So yeah, among all magnetic fields, we have the magnetic fields that have nested flux surfaces. And we all know that nested flux surfaces are not sufficient to confine a plasma. So we're going to need homogeneity. And thanks to Eduardo, I don't have to describe this in more details. Now, homogeneity comes in three flavors. It comes if your line of constant magnetic field strength are closing poloidally, helically, or toroidally. And this is what I show with these three sections. Now, Eduardo talked about the famous QI class of equilibria. And we all know also the sub class of quasi-symmetry with QP, QH, and QA. Just to be as complete as possible, I'm just going to remind you what is QA, so quasi-axisymmetric. And here I have the famous design of Langermann and Paul, where despite having a three-dimensional magnetic field, when you look at the field strength in Boozer coordinates, you don't have any dependence on the toroidal Boozer angle, zeta, and so that's what we call quasi-axis symmetry. Now, you all know this, but I want to point to one thing, is when you look at the experiments, so this is not an exhaustive list of experiments, but most of the experiments, well, most of them, we have them as nested flux surfaces. I categorize them here. And you can recognize a few of them, like W7A or W7AS, that are the predecessor of W7X, or CNT, that is the Columbia Non-Neutral Torus, which is the stellarator we have currently at Columbia. Then when you look at the optimized stellarators, well, we have only W7X, that is QI. And I wrote here Stellaris, which is the proposed design by the Proxima fusion company. And it's even worse when you look at quasi-symmetry. We have one that is quasi-helically symmetric, HSX, of course, and one that is QA, that is Muse. And this is a small-scale stellarator at PPPL. However, there's interest in QA. You have the EPOS design from the Apex group at IPP Garking. CFQS, that's the Chinese first quasi-symmetric stellarator that is currently being built. And this is EOS. I think this is the proposed design by the FEA fusion company. So to complement this graph, what we want to do is take CNT, that is, I remind you of the Columbia Non-Neutral Torus, and re-optimize it to bring it into QA. And that's the CSX stellarator. So as a starting point, I'm going to show you what is CNT. On the right, I have a picture of CNT in the lab, when the lab was in order. And on the left, I have a 3D version of CNT. So what you see is these two large planar copper coils, circular copper coils, that we call PF coils, for poloidal field coils. And then we have the vacuum vessel. And this vacuum vessel is slightly particular because it's not conformal to the plasma boundary that you can see on the right. Inside this vacuum vessel, we have two additional coils that we call interlinked coils because they are interlinked. And these are also planar copper coils, and they are water-cooled. Now, what we want to do is reuse all of this, excepted the interlinked coils. So we want to remove the interlinked coils, re-optimize them, wind them with non-insulated HTS technology, and have a quasi-axisymmetric plasma in there. The goals of CSX are threefold. So the first one is, the first category of goals is regarding the physics. So regarding physics, we want to look at quasi-axisymmetric physics. And in particular, we want to look at reduced neoclassical flow damping in the direction of symmetry. That's something that was done about 20 years ago in HSX, so for QH stellarators. And you see here a plot where they measured the flow induced by a bias, an electrical bias in the plasma for two configurations. So one is QHS, close to quasi-symmetry, and one is the mirror configuration further away from quasi-symmetry. And they showed that you have a higher flow when you are closer to symmetry. So this is something we want to replicate in quasi-axisymmetry. And then we are thinking also of looking at MHD stability, in particular the importance of the magnetic well, and potentially turbulence measurements. So CSX is going to be a low temperature, low density plasma, so you can stick probes in there without burning the probe. And so you have like high resolution measurements available. The second set of objectives are engineering. So as I said before, we are going to wind the coils using non-insulated HTS coils. So basically that means that you use HTS tape and you don't put an electrical insulator between each layer of tape. And I will come back to this later to explain why it is so interesting. But multiple people and companies are interested in this. Here I have a picture of our first prototype, and on the right you have a picture from the Wall Street Journal on some prototype from Proxima Fusion. So you see that Proxima is also interested in this kind of technology. So really our goal with CSX is to demonstrate that it is possible to use this kind of coil technology in a stellarator environment. Also, we want to apply some of the recent developments in stellarator optimization to come up with a practical device. So this is trying to apply all the developments from this collaboration and people outside this collaboration to a new design. Finally, one set of goals is education. You've seen at the beginning, we have many graduate and undergraduate students that are collaborating on this. And you see here a picture of the team at one point in time. This is constantly evolving because students are coming from one project and then leaving. But since I joined this team about a year and a half ago, we had maybe 25 students already interacting with us and being exposed to the field. So yeah, the goal is to train new scientists and engineers and do outreach to new generations of undergraduate students. Okay, with that, I hope I convinced you that having a new experiment would be beneficial. And now I'm going to jump into the details of how we optimize this new experiment. And to really explain the optimization, I first need to describe the engineering, because as we will understand, the engineering is constraining a lot what we can do with the optimization. So we need to understand the engineering first. Then I will discuss different approaches for optimization, and that will lead me to identifying some constraints and physics objective for CSX. I will show you some configurations of interest and how we refine those solutions. And I will conclude with some remarks and a very long list of future work. Okay, so let me jump into the CSX engineering. Here I have a nice plot made by the engineering team to try to show you how the coils are looking. And I think it's easier to look at in real life, so I'm going to give you this to pass around. This is really the first prototype, so it's 3D printed in plastic, and you have a filler tape in there to see how it's done. But basically, the goal is to 3D print the coil and to have winding tracks. Okay, I'm going to come back on this. Winding tracks in which we put the HDS tape in there, right? So I'm going to give this around. You can have a look while I talk. So as I said, the coil technology, we're going to 3D print the body of a coil. And in this 3D print, so this is a cross-section of the coil. In this 3D print, there are two trenches in which we're going to put the HDS tape. And here the HDS tape, I show it with these red bars, right? In between those red layers, we're going to have solder potting that gives structural integrity to the entire thing. And then around this 3D printed coil support, we have another layer that is going to play the role of a cryostat and the support structure. And this is, well, important to keep all of this in superconducting temperature. Now, the advantages of this technology is that it has an inherent protection to quenches. You can imagine that if you don't have an insulator around your tape, if locally your tape does not becomes non-superconducting, the current can self-redistribute around it, and you don't have a catastrophic quench. It is mechanically robust, but it has a large self-inductance, so you can have a relatively long charging time. That's something you have to pay attention to. In our case, we don't really care about this because it's a stellarator, so we can take a long time to charge it. We don't really want to have active control or something with this. Regarding CSX coils, we are looking at double pancakes, so as I show here, or quad pancakes, that would be with 4 winding tracks. With either single wind or double wind, so that's how many tapes are getting out of the winding pack. And we are looking at coils that would carry about 400 kiloamps for a field of roughly 0.5 Tesla on axis. All of this has to be cooled to 20 to 40 kelvins by conductive cooling. So this means we have a very cold thing called a cold head that we stick to it, and we hope it's going to suck all the energy out of the coil. And as I said, we are using solder potting between the tape. This is what the engineering team has been up to in the recent year, building a test bench for the very first coil, 3D coil that we have wound in the lab. Very quickly, the idea is to have a big tank, a vacuum tank, in which you have a coil connected both electrically to a power supply and to the cold head that cools it down to cryogenic temperature. And then all of this thing is in a barrel surrounded by liquid nitrogen to keep it as cold as possible. So all of this is ready. I heard today that we still have some issues with the cold head or with the cryogenic technology, but soon we're going to have the first results to see how our first prototype is dealing at generating the field. Here is the first prototype. So the coil you have walking around is exactly the same as this one, but this one is 3D printed in metal. So we're using this aluminum alloy, and it has been wound with superconducting tape, so it's ready to be tested. Now, when we made this coil, we realized that the tape is the winding is very difficult in this region because it's both concave and has torsion at the same time. So the tape really likes to just get in a very weird angle, and that's not what we want. So we are working on a second prototype that you have here, where we have concavity of the tape in this region, but not torsion, to see if we can do that. And you see behind here the test bench I was mentioning before. This is the big vacuum tank in which the testing will be done. With that, I think I have given you enough info about the engineering, so I'm going to go to the optimization. The first idea you can have to optimize CSX would be to look at a two-stage approach. And no surprise, this is not going to work. So as a reminder, the two-stage approach goes as follows. You start with a stage one, where you optimize your plasma boundary, that I call gamma, for all your plasma objectives. So in our case, it would be quasi-symmetry, a specific volume, rotational transform, aspect ratio, you name it. And you run your optimizer, you find a very nice plasma boundary, and you're really happy with it, but you have to find coils that generate a magnetic field that is everywhere tangential on this magnetic surface, but also that satisfy the engineering constraints. And that's where the trouble begins, because you're not going to find, in the case of CSX, coils that can generate this beautiful plasma surface that is in red. So this is a typical run I did using the two-stage approach. You see that the coils are fitting within the vessel, so this is one of the most difficult engineering constraints to satisfy in our case. But the field they generate, that you see here with the Poincaré plot, so in black, is absolutely not matching the target boundary that is in red. So this does not work. You can think of changing your stage one, adding different terms, changing the weight, trying to make it work so that then you can find coils that match this. But this is exactly what the a single stage optimization would do for you. So instead, we forget about two-stage approach, and we're going to use a single stage optimization approach. Now, luckily, in the recent years, two people in this collaboration have proposed different single-stage optimization approaches. Rogerio, George, proposed what we call here the VMAC-based approach, and Andrew Giuliani proposed what we call the Boozer surface approach. So let me just go quickly through these two approaches and tell you some of the pros and cons about them. So for the VMAC-based approach, well, the goal is, what you do is that you optimize both your coils and your plasma boundary degrees of freedom at the same time. So you explore this huge parameter space in a single optimization loop. And for each plasma boundary, so each set of gamma doves, you are going to use VMAC to evaluate your plasma objectives. And then the coupling between your coils degrees of freedom and your plasma boundary degrees of freedom is done by minimizing the quadratic flux. And here I use the normalized version of it. So basically, you minimize the component of a magnetic field normal to your target boundary everywhere on the surface. The full objective that you minimize then depends on both the coils degrees of freedom and the plasma degrees of freedom. And you see that you are trying to minimize a plasma objective, coils, engineering constraints that are in this F coils, and then this quadratic flux that is providing the coupling between both. The issue with this approach is that your parameter space is going to be huge. And if you use VMAC, you have to do finite differences to take derivatives of F plasma. And that generates numerical noise and is troublesome for optimization sometimes. Of course, if you change VMAC for desk, for example, you wouldn't have this problem because you have access to derivatives. In our case, we have found that the VMAC-based approach is less robust and works less good than the Boozer surface approach. So for every result I'm going to show in this talk, we're going to use the Boozer surface approach. If you want some details about results that we obtained with the VMAC-based approach, they are in a paper that we recently published on the topic. So for the Boozer surface approach, now we are going to optimize only the coils degrees of freedom, so we have a smaller parameter space. And then for a given set of coils, we are going to solve a PDE in the least square sense. And the solution of this PDE is giving us a magnetic surface in the field generated by our coils. The coupling is given by the residual of this PDE. So if you solve exactly your PDE, you do find a magnetic surface, and you have a good coupling between the coils and your surface. If R square is large, well, then the surface you use to evaluate your plasma objective is completely off. And then your objective is then given by this function that depends only on your coil's degrees of freedom. And you see that you still have your F plasma that depends on your boundary, and your boundary itself depends on X coils. We have our coils engineering constraints and this F residual for the coupling. Now, the issue with this is that it only works for vacuum fields. So if you want to build a reactor, no luck, you cannot use this. But for our case, CSX has a very small value of beta, so we can use this without issue.